let's take a look at how work and energy affects rigid bodies. The big equation we use is called the principle of work and energy equation. It has three parts: the initial kinetic energy, the sum of all the work that's being done by the forces affecting the object, and lastly, we have the final kinetic energy. Let's break down each component. Kinetic energy can be broken into three broad groups. First, we can figure out the kinetic energy of a rigid body that goes through only translation. Translation simply means that the object is not spinning when moving from one point to another. Since it's not spinning, angular velocity is zero. So for that, the equation is half times the mass of the object times the velocity at the center of mass squared. Now let's say we have an object that's rotating about a fixed axis. That means angular velocity is not zero. In that case, we can find the kinetic energy by using this equation. We have the kinetic energy when an object is translating, plus we have a new part, which is the mass moment of inertia about the center of mass times the angular velocity squared. If, however, instead of using the mass moment of inertia for the center of mass, we find it about another point, for example point O, then the equation becomes this. Lastly, we have the general plane motion of a rigid body. In that case, we use the same equation as before and use the mass moment of inertia about the center of mass. If you go through the steps to find the instantaneous center of velocity, you can actually write this equation in a simpler form like this. In this case, we're finding the mass moment of inertia about the IC point. Now that we know how to find kinetic energy, let's talk about work. Work is basically force times distance, and I cover this in detail in the kinematics video about work and energy. So I will glance over the stuff we need for rigid bodies. Let's say we have an object like this, and we apply a force at an angle. The work that's done is force times cosine theta times the distance traveled. This is when the force is a constant. If it's a variable force, we can integrate it like this to find the work done. When we consider an object that's moving up or down and think about the work that's being done by the weight of the object, we can figure it out using this equation. Delta y is the vertical displacement. If the object moves downwards, it's positive work, and if it moves upwards, it's negative work. This is because weight is opposite to the displacement. Next, we got the work done by springs. If we have an object attached to a spring like this, and we pull it to the right, the spring will create a force where it's trying to bring the object towards the left. The work that's done by the spring can be found using this equation. S is the elongation or compression of the spring, and K is the stiffness of the spring. The last factor we need to consider is work done by a couple moment. If the moment is not constant, we can figure out the work done by this equation. The initial and final theta values are in radians. So if we have an object like this, and due to a moment it spun 90 degrees, then the lower bound would be 0 and the upper bound would be pi over 2, since that's 90 degrees in radians. If the moment is a constant, then we can figure out the work being done by this equation. You should also note that some forces will do no work. For example, if we have an object pinned like this, the reactions at the pin won't do any work since the pin is fixed. Another example would be when something rolls along the floor, but it doesn't slip. If it doesn't slip, the friction does no work. And of course, if the force is perpendicular to the displacement, it does no work. In other words, let's say an object moves only in the horizontal direction. Then vertical forces will do no work since the object doesn't move up or down. So again, a force only does work when it moves through a displacement in the direction of the force. For some questions, you need to figure out the mass moment of inertia for objects. I show some formulas here, but you can find many more online by searching for them. Now let's get started with some examples to see how and when to apply the equations we talked about. Let's take a look at this problem where we have a rod at rest. Then a force of 150 newtons is applied to the bottom of the rod, and we need to calculate the angular velocity when it rotated 90 degrees. Let's draw a free body diagram of the rod. We have the reactions at pin O, so this is a rotation about a fixed axis. We also have the weight of the rod at the center, and let's not forget about the 150 Newton force applied at the bottom. To solve this problem, we're going to use the principle of work and energy. Let's write down the equation. We will do each segment separately and then plug everything in. So first, we need to think about the initial kinetic energy. The whole system starts from rest, which means initial kinetic energy is 0. For the final kinetic energy, Since this is a rotation about a fixed axis, we can use this equation. But to use it, we need to figure out the mass moment of inertia for this rod at point O. So for that, the equation is this. It lets us calculate the mass moment of inertia at the end of a rod. Since point O is at the end, we can use this equation. So we have a mass of 10 kilograms and a length of 3 meters. Let's solve. Let's plug in the mass moment of inertia we found into our kinetic equation and set it aside. Now we have to consider work. The work is done by two forces, the weight and the 150 Newton force. The reactions at pin O does no work since they don't move. The two forces that do work are both constant, so we don't need to integrate. First, we will focus on the 150 Newton force, which does positive work since it's pushing the rod where we want it to go, which is clockwise. So remember, work done by a constant force is force times distance. So what we need is the distance for which the 150 newtons acted on the rod. We know that the rod turns 90 degrees, and in radians that's pi over 2. And we can find the distance by multiplying that by the length of the rod. Or rather, think of it as the radius. Think of the end of the rod drawing a circle, so it's just the arc length we're trying to find. Now we can figure out the work done by the 150 Newton force. Next is the work done by the weight, which is negative since it's trying to push the rod counterclockwise. For that, it's simply weight multiplied by the displacement, which is 1.5 meters. Now all that's left is to plug in the values. Let's solve for the angular velocity, and that's our answer. Let's take a look at this problem where we have a disc attached to a spring. Then a couple moment is applied to the wheel and we need to figure out how far the center of the wheel will travel before stopping. Let's draw our free body diagram. We have the weight, the force of the spring, the moment, and the normal force. Since the disc rolls without slipping, we don't need to worry about friction for this question because it does no work. Now let's write our principle of work and energy equation. For the initial and final kinetic energies, they will both be 0 since the disc starts from rest and stops at the end. Now two forces will do work, which is the spring force and the moment applied to the disc. To figure out the work done by the moment, we need to figure out the theta value, or in simple terms, how much the disc will turn. Since as before, this is arc length, we can write our distance like this. Let's isolate it for theta after we plug in the radius, which is 0.5 meters. Now we can figure out the work done by the moment. We know the moment from the question and we wrote the theta value in terms of the distance moved. Let's simplify. Now for the work done by the spring. Since the spring is trying to stop the wheel from going forward, it does negative work. Let's write the formula for work done by a spring. So the stiffness is given to us and the distance it stretches is the length the wheel travels. All that's left for us to do is plug in all of these values into our work and energy equation. Solving this equation will give us two values, 0 and 1.6 meters. It's definitely not 0 meters, so the answer is 1.6 meters. Let's take a look at one last question where the moment applied is not a constant. We have a disc and we need to figure out the angular velocity after it goes through 2 revolutions. Let's draw a free body diagram. We have the weight, the reactions at pin O, and we have the moment. Now for our principle of work and energy equation. The initial kinetic energy is 0 since everything starts from rest. To find the final kinetic energy, we need to use the equation for kinetic energy and rotation about a fixed axis. For that, we need to find the mass moment of inertia about point O. Since point O is the center of this disk, the equation for a uniform disk works. The mass is 20 kilograms and the radius is 0.3 meters. Now that we have the mass moment of inertia, we can figure out the final kinetic energy. For the work that's being done, only the moment applied will do any work. But notice how it's not a constant value. So we need to integrate. The lower bound is 0, but what about the upper bound? Well, we're calculating it at 2 revolutions. One revolution is 2 pi, so 2 revolutions would be 4 pi. Let's solve the integral. Now we can plug our values into the big equation. Let's solve for the angular velocity, and that's our answer. That should cover the types of problems you will face when it comes to work and energy with rigid bodies. If you found this video helpful, please consider sharing it with your friends and classmates. Thanks for watching and best of luck with your studies.